Welcome to the first day of class. We are in Chemistry 111, General Chemistry, and as you know, we are not meeting face-to-face today. Um, so this is a way for me to introduce you to myself and kind of give you some instructions virtually and then get you started on the chapter 1. So hopefully you can, if we met face to face, we would discuss the syllabus. Um, so make sure you log into your Blackboard and read your syllabus and bring any questions you might have regarding the points in the class and the calendar. You can also access this under your documents under course materials and look at your due dates and highlight exam dates. If you have any conflicts, you need to send me an email and we can work out things. We also have online quizzes. So if you look at your quizzes and the quizzes, those dates and the point values, you can ask me questions about that. And like I said, we'll answer questions the next time we meet face to face. Today, the purpose of this will be about 20 or 30 minutes of a lecture in which you can start on the material. You also want to log on to your online homework, and you should be able to access that link through your Blackboard for the course material. You'll want to get started on your homework. Those due dates are already set online. You don't have to wait to start working that. You also have your textbook to access online. And like I said, because I expect that to be 30 to 40 minutes for you to review and look at those things, then we'll start on this chapter now. I hope that you would take notes, and this might be 30 minutes discussing your new chapter, chapter 1. So just an introduction to me. This is me right there. My name's Dr. Thomas. I am a University of Washington fan. This is my family. So this is my daughter Sarah, and she is a sophomore at University of Washington. She is a pole vaulter. And this is my husband, and we have a blended family. So I also have Mary. This is Mary, and Mary is a senior at EKU, and she'll be going to physical therapy school at UK. We're very proud of her. And this is Paul, and Paul is my stepson who is in high school. This is my husband, Mark, and he has a PhD in biology. So he likes biology. And this is Nathan. This is my daughter's boyfriend, Nathan Green, and he actually won the 1500 men's meter, 1500 meter NCAA last year. So, and he's from Idaho. So that's my family. I grew up in northern Kentucky. If anybody knows Carrollton or Carroll County. I got a bachelor's degree at UK. And then I actually wanted to do cancer research. So I ended up getting a master's degree in organic chemistry at the University of Louisville, in which I then worked at Eli Lilly for 6 years. But then when Sarah was born, I switched over to teaching. And so in order to teach organic chemistry and chemistry in college, I had to go get that PhD. I like learning, so when Sarah was little, I was working on my PhD at the University of Kentucky. So I've been teaching now chemistry in college for maybe 8 years. So something interesting about me, I ran the Boston Marathon in 2006. And so what I would like for you to do is get out a piece of paper, and I would like for you to tell me who you are and kind of where your family and where you're from and what's your plans. And so I would like for you to put that in your class folder. I will give you a class folder, and make sure you print your full name on there so I can give you credit. All right, so let's talk about chemistry, folks. Chemistry is the study of matter, its properties, and the changes that matter undergoes, and the energies associated with these changes. So let's look at matter. Matter is something that takes up space and has mass. Everything, folks, everything that you touch and see, and even things you can't see, are made of elements that go in to make compounds. Okay? And you can find these all on the periodic table. So next time I see you, I'm going to give you a periodic table, and I expect you to color that periodic table and label it. So we're going to see that in the next slide. I don't wait till chapter 2 to introduce the periodic table. You get that the first week. And you'll get to use this periodic table for all your online quizzes and homework and in-class discussions. Now, so you're going to see different elements. I expect you to learn a lot of these elements. We'll talk about which ones those are. But like if you take hydrogen, that's your first element, hydrogen. Now, chemists are lazy. They don't want to write the word hydrogen, so they just write H, okay? Then you have helium, okay? They'll just write He. Now, let's say you have carbon. So carbon, they'll just write C. And you'll learn that like 1 carbon and 4 hydrogens. This is a chemical formula. And this is methane. So if you've ever heard of methane gas, this is methane gas. And you can write the word methane, but it's also CH4. And that means every carbon has 4 hydrogens. You see the little subscript there? And so this is a compound. Okay, so that is a compound. This is an element. Carbon is an element. Hydrogen is an element. So the periodic table of elements are these 1 letter, sometimes 2 letters, right? Helium. Notice the second letter is a lowercase. Okay, so that means this is 1 element. So that's why it's very important that you capitalize the letters that are capitalized, because that represents an element, and the lowercase need to be lowercase because they belong to that first capitalized letter. Now, elements combine to make compounds, and those compounds have different properties. So if you think of carbon dioxide, so this is carbon dioxide, and it's Di, we'll learn that in chapter 2. Dioxide means 2, dioxide, carbon dioxide, you see the 2. This is different than carbon monoxide. So you'll see that both of these have a carbon and oxygen element, see they're capital letters, but carbon dioxide has 2 oxygens where carbon monoxide has 1. Now they have different properties, okay? So this will kill you. It will bind to your hemoglobin and suffocate you because it binds so tightly to your iron that your iron and your hemoglobin in your blood cannot exchange to get oxygen into your cells. And that's why carbon monoxide is very deadly. Carbon dioxide is what you exhale. So like if I breathe in, I'm breathing in oxygen, O2. When I exhale, I'm exhaling carbon dioxide. So what I want you to understand is, yes, chemistry is the study of matter, its properties, and the changes it undergoes. And so as a chemical, like I did organic chemistry, right? So I was trying to make drug molecules for cancer research. And so I would basically, I could take something like I could take a compound that has, maybe, let's say methane, and I could react it with bromine. And bromine, if you look at the periodic table, it's Br, it's actually a liquid. And bromine is very bad for you, this liquid. But then I could combine these two in a flask. I could put these in a flask in the lab and put those elements and compounds in there. And then I can make something like this, okay? And so then I make a new compound. And you actually make HBr. So we're going to learn about how to balance reactions, but this is called a chemical reaction. So you have something at the beginning, that you put into your flask. It's kind of like cooking. When people ask me, what do I do all day? It's like cooking. You put this into your flask. It's like putting it into a pot, and we call these reactants, okay? And then these are your products. This is what you get out. And then a lot of times, and you can control these things. So you need to, those are chemical reactions. They break bonds and make bonds, and a lot of times they'll give off energy. So this might give off some energy. And we can also do different things with that energy. So this is chemistry, and the nice thing about chemistry is we have a periodic table. So like I said, I'm going to hand you a periodic table the next time we're in class face to face, and I want you to get some colored pencils or highlighters, and don't make it too dark, but you're going to want to do your labeling. See all this right here? So you have I want you to make a legend. So, and you can do this for chapter 2 as well. And I will give you a 2-point exam 1 bonus. So I will take your name down and put a check mark, which would be 2 points on your exam 1. If you show me, all you gotta do is show me this labeled periodic table. Okay, so maybe you come see me after class, but I want you to I want you to label this group 1. So group goes down. You can find this information in chapter 2. Group goes down or up and down a row, and then a group vertical. So groups are vertical, and then rows go across. So they go across. And so we're just going to talk about the group. So group number 1, and you see this 1A. So group number 1 right here, these are called the alkali metals. And then group number 2 here are the alkaline metals. Now you see how alkaline is a longer word than alkali? So that's how the second column, see, is kind of like bigger, right? So ein, alkaline, bigger word. Those are the alkaline metals. This area here, I always think of it like a choo-choo train, are the transition metals. So I call that the transition metals, and this is the way I want you to label. So if you choose transition metals, and then you could choose yellow, you could choose green. So you make a legend, right? Choose red for those. Now keep in mind, these are all metals. Metals, metals, metals. 2/3 of the periodic table are metals. And so we're going to talk about what those properties are with metals versus non-metals. The other thing I want you to see is, see this line here? And you can label that. That is, those are, what do we call that? I'm drawing a blank here. There's stair step. They're, I'll have to come up with the word. For some reason, I'm drawing a blank here. Oh, I know what they are. They're metalloids. Metalloids. You have to look and see if I spelled that word right. Metalloids means they have some properties of metal plus non-metal. So this is the transition to the non-metal. So that means these, see all the yellow? These are non-metals. Okay, so these are non-metals. That's going to be important because non-metals you're going to find in compounds get negative charges. Okay, so I'm going to say always when you're in a compound, an ionic compound, we'll talk about that, they'll get a negative charge, where all these metals get positive charges. Okay, so they're metals, they get positive charges. And we'll talk about what that means. The other thing I want you to list is this right here, the last one. Those are your noble gases. And then I also want you to write here, these are your halogens. So what do we have here? Labeling 1, 2, 3, 4, 5, 6, 7. So there's 7 things to label, and you can ask me questions about that. But I want to introduce the periodic table to you because each one of these elements, like aluminum, this is what things are made of. Carbon, most of the things in organic are of the organs, so they're carbon. So carbon, usually nitrogen, oxygen, phosphorus, sulfur, hydrogen. Those are what our DNA, our bonds are made of, our food. Where is gold? AU. AU, it has 79 protons. And where's lead? PB, 82. And so, as you can see here, the blue here are metals, metalloids. There's the spelling of the word, are these green, so they're in between. You see these are the metalloids here. And then the non-metals here, including this, are non-metals. Okay. All right, so in chapter 1, this is the breakdown of chapter 1. We're introducing some fundamental definitions. We'll look at the scientific approach, and then we'll talk about measurements. We'll talk about, we'll finish that up for chapter 1. Today I'll go over SI units and measurements. We're also going to talk about different phases, which is the gas, the liquid, and the solid. So if you look at this here, you can see this is a substance called lead. This is a substance called gold. And so you can write gold or you can write AU. Lead is LEAD or PB. This is where the word plumb comes from because it's a lead pipes. It's a Latin word, gold. But using your periodic table and everything you can observe, make observations, what's the difference between these? So you could say that they're both metal, right? They're both metal. One is shiny and colored kind of yellow. The other one's kind of dull. And so we make observations about different characteristics. Now my question, could you convert lead into gold? So that is what the alchemists wanted to do, because if you had gold, right, and you create gold, then you are wealthy. So could you convert lead into gold? Well, let's look at the periodic table. So 82 protons and 79 protons. So that's the difference. Did you know that if you could subtract, so if you could minus 3 protons from the nucleus of lead, then yes, you can make gold. Okay? This is called nuclear chemistry. We won't be talking about nuclear chemistry in here, okay? But that's what nuclear chemists do. They, and you've probably heard of E equals MC squared, and you've probably heard of the nuclear bomb. Okay, so you know that that generates a lot of energy. The sun, what is the sun? The sun is 2 hydrogens fusing together their nucleus to make helium, and then that's called fusion. And then helium splits into two hydrogens, which is called fission. So it's a fission fusion nuclear reaction is the sun. That's where we get all of that sunlight energy. So nuclear chemistry changes the number of protons. And when you change the number of protons, yes, you change the substance. But you see how the properties of lead versus gold are different. And so this is chemistry. And so the scientific approach is like what we do. We make observations. So we just made some observations. We talked about the difference between gold and lead and their properties. And then we asked the question, can we convert lead to gold? And then you'd have to do a nuclear experiment and see if you can do that. And then you would observe and then do another. So you just make more observations and then you recorrect, do another experiment. And this is the scientific approach. Okay, so like I said, we were going to do some definitions. So matter is anything that has mass and volume. And we're talking about the properties give the substance its unique identity. Okay, so the other thing I want to talk about, what is the difference between a solid, liquid, and a gas? A solid has a fixed shape, okay? So you can look at these molecules is very close together, okay? So this would be a solid. And then a liquid, what happens is you're dealing with the same molecules, okay? But now they're further apart in space. Okay, so this would be liquid. And then a gas, they're even further apart. Now, let's give a compound. Let's make this water. H2O. Now, water is H2O. Okay, so this is water. You notice water. H2O is water. This is the structure of water, which we'll learn towards the end of this school year, how to draw these structures. This is the structure of water. Now, we know that when it's a solid, it's ice because it's very close together. Okay, so it's very close together. That makes it, but it's still H2O. Then if you heat this, if we add heat, then these molecules are going to bump into each other. Okay, this is called kinetic energy. Kinetic energy is like if you start jumping in space and you're in that movement. So these molecules are always moving. Now they're bumping into each other. They're generating some momentum and they're spreading apart. But they're still H2O. Okay, the substance is the same, but now they're liquid. And if you add more heat and now they get so far away, they become water gas. And they have no fixed shape or volume. So it's still the same substance. This is called a phase change. And I want you to remember phase change equals physical change. Okay? So because it's not a chemical change. A chemical change, you'd have to change the substance. You change the substance, you change the formula. These formulas, whether they're liquid, gas, or solid, are the same, H2O. So that's what they're showing you here. Solid molecules are the same. This is ice, all three phases. You got the gas. This is water, H2O. You got the ice, and then you have the liquid. And it's just a matter of how far apart are these water molecules to one another. So physical properties, that means the chemical substance is the same, remains the same. Color is a physical property, melting point, boiling point, density. Water boils at 100 degrees Celsius. Water cools at 0 degrees Celsius. The density of water is 0 grams what is the density? Mass over volume, so gram over milliliter. So that is the density of water. Now, chemical properties, you change the substance, okay? You got to change the substance. So let's look at iron. Iron, you know iron. Cars made of iron. If it reacts with oxygen, then you get iron oxide. Iron, let's see, 1, 2, 3, 4, 5, 6. This is iron 3 oxide, which you'll learn next chapter on how to name these. So iron 3 oxide is rust, okay? Rust looks very different than iron. It has a chemical change. If you leave iron unprotected, meaning no paint, in an oxygen atmosphere, you're not going to have iron anymore, and you're not going to have oxygen. You're going to have a new substance called iron oxide. And so those are chemical changes and chemical properties. So remember, physical change, phase change is a physical change. Chemical change, you've got to change the substance. So this is showing you solid water and liquid water, but a chemical reaction, you have to break those bonds and form new bonds. And that's what they're showing you, this electrolysis with hydrogen and oxygen gas are making water. So you got hydrogen, you see the two molecules of hydrogen. You have oxygen, this is oxygen, this is hydrogen. And when you add those together, you make water. So a lot of times in your book, you're going to see this is a representation of an element. Now you do have some diatomic elements. They make actually the number 7. There's 7 of them. You kind of make the number 7 on your periodic table. See if you can see the 7. Okay, so there's hydrogen, and then there's nitrogen, and then there's oxygen, and then there is fluorine, chlorine, bromine, and iodide. See, 1, 2, 3, 4, 5, 6, 7. There's your 7. Okay, these are called diatomic elements. Okay, and so you can see here, this could be a representation of any of those diatomic elements, like oxygen. This would be like sodium metal, could be carbon metal. You know, it's a non-metal. Let's just stick with the monatomics, like magnesium. So this could be a single element. And so they're showing you pictures of elements. A compound is a substance that has atoms of fixed in fixed proportions. So this could be like PCl3, which the purple could be phosphorus, and it has 3 chlorines. So that could be chlorine. So if you had phosphorus, which is like, and you had chlorine, and you combine these together to make PCl3, that would be 2, 6, and 3. You'll learn how to balance reactions. So this is your reactants. This is your product. So you can convert these, phosphorus and chlorine, you can combine them to make a new substance, which is phosphorus. You'll learn how to name these next chapter, trichloride. And that would be something like that. And that's so that you can see the different colors, and they're trying to represent a new compound. A compound cannot be separated by simpler substance by just any physical process. Okay, so here's like a mixture. This could be oxygen, this could be sodium, this could be phosphorus trichloride. And you can see that now that's a mixture because it's a combination of 2 or more substances. These can be separated. A mixture can be separated by a physical process, okay? So this is using a magnet to separate iron from sand. Sand is SiO2, and iron is Fe. So iron, since there's only one of them, could be represented pictorially like that. And then silica dioxide could be represented like this. And so you can imagine that these can be separated by their properties. And so one of the properties of iron is that it's magnetic, meaning it is attracted to a magnet, and you can use a magnet to separate the two. And so here you want to, in your notes, just look at these and try to decide if there's a physical change or a chemical change. What I like to do is look at the periodic table and say, okay, can we look at these and see if we can come up with something like could this be like H2O, and the H represents with 2 red and the O is blue. You see how they're all connected like a compound? And then here, this would be like, okay, that would have gone to like HO, and that would have been O2 or H2. You see how that's they're new compounds now. So these are new compounds. So this would have to be a chemical reaction. This is a chemical change. Here, they're still all intact. You see there's 2 reds and 1 blue. And so what happened between A and C is they got closer together. Okay, so this could be a liquid and this could be a solid. So that would be a physical change, because you can see that that still looks like it's got 2-to-1 ratio, where these ratios have changed. And so A to B, like we said, was a chemical change because the ratios have changed. And then A to C would be a physical change because the ratios are still the same, so their compounds are still the same. They just got closer together. Which of the following statements is correct? So see if you can figure that one out. Okay, so it's not going to be sodium metal because that would just be one element. If it was sodium chloride, it would have to be something like 2 elements, and they would be 2 different colors. A mixture of 2 elements, no, because there's not other. Could it be one of the diatomics? Yes. Okay, so a physical change, the composition does not change. It can be reversible by changing the temperature. We can melt ice. You just add heat. You can then cool the water, the liquid, and you can then make ice. So it is reversible by change of temperature. Other properties, physical properties, are malleable. Now remember, most of these things are metals. Metals are good conductive for electricity, and you can shape them when things are malleable. You can shape them into the shape you want. They have properties such as melting points and boiling points and densities. Chemical properties, you're changing the substance, so you're having to do a reaction. And so these reactions are changing the compound. So the compound is going to change. Such chemical properties you might see bubbling, acid, gas being formed. So you can kind of go through those. I'm not going to talk too much about this, but energy in chemistry, there's 2 forms of energy, potential energy and kinetic energy, and you can change one form of energy into the other. Potential energy, like in your food, there's chemical bonds that you break. So when you eat and what you're doing, so like if you eat a lot of fat, okay, it's a lot of carbon-hydrogen bonds. And when you eat them and you convert them to physical energy, like to go running or something, and you exhale, you're bringing in oxygen, And you're reacting each one of these carbons with oxygen. So you exhale carbon dioxide. And so you're converting food energy in these chemical bonds. You're doing a chemical reaction to physical energy. And that's considered potential energy. And it gets converted into potential energy in the food before you eat it, gets converted into kinetic energy. All energy is conserved. That means it has to be converted from one form to the other. A physical way of looking at this is if something is up high and then it falls down, this is your potential energy because it has height. And then it goes down, it has turned into kinetic energy. And so that's the conversion of energy. And we'll talk about that later on in other chapters, and we'll actually do mathematical equations for that. Opposites attract, so a negative charge and a positive charge will be attracted to each other. And this is actually showing you the potential energy. You've heard of octane, so that's 8 carbons. So let's see what that is. 1, 2, 3, 4, 5, 6, 7, 8. So that's 3, 6, 7, 8, 18. So this is octane, which is gasoline. And so the same thing is happening in your body as in your combustion. You react this with oxygen and you add, the heat. And what it does is it converts this to CO2. That's why you have to have a catalytic converter to make sure you don't get any carbon monoxide. You get a full conversion to CO2. This gas will actually move the piston up and down and will cause that car to move from point A to point B, and that's kinetic energy. So the potential energy of the gasoline gets turned into the kinetic energy of the car. Okay, so this is where I want to leave off, and I want you to start writing these down and learning your SI units because you will need to know these, and you'll have to have them memorized. I want you to know that any form of gram or kilogram means you're measuring mass. I want you to know length is measured in meters, and we'll look at meters, we'll look at centimeters, we'll look at millimeters, and so we're going to look at that. Time is measured in seconds, so if you see second, then that's time. Temperature, I'm just going to do degrees Celsius and Kelvin, so I do want you to be able to change from degrees Celsius to Kelvin, so we'll talk about that. We'll talk in chapter 3, we'll talk about the mole, and we will not do the other two. So which of the following statements is correct? Mass is measured in grams, right? Milliliters is what? That's volume. And Kelvin is temperature. So you need to know that because when you get a word problem, you'll see Kelvin, you'll be like, okay, we're dealing with temperature. Oh, grams, we're dealing with mass. Oh, milliliters, we're dealing with volume. Okay, so this is where I will start for your class. I want you to know mega, kilo, deca, deci, centa, milli, micro, nana, and that's about all I go. You might as well go pico. So these are the ones I go. These are the ones that I expect you to know. Okay, and I want to, now what I do is this is how I memorize it. Big number with small prefix. Okay, now you might have had a new way, a way your teacher taught you how to do it, and I'm going to tell you, do it my way, because you'll see, it won't work. at some point. But so like if you want to memorize deci, so here, you see this right here, the 1. Everything below here is small, okay? So this means the prefix is small. The prefix is small. Everything above here, the prefix means big, okay? So I don't even do deca. So basically I don't do hecka. So basically you just need to know these two, mega and kilo. Big M and then kilo. And that means they're bigger than the base unit. And this is your base unit. These prefixes, deca, centa, milli, micro, nana, and pico, they're small prefixes. And you see how they're little letters? Minus this K for kilo, these are all little letters. And what does deca mean? A decade means 10. Centa means a century, which is 100. Milli means 1,000. Micro, see this is 3 zeros. Micro is 6 zeros. Nana is 9 zeros. Pica is 12 zeros. Okay, so you see the pattern, 3, 6, 9, 12. Here, kilo is 3 zeros, and mega is 6 zeros. So if you do a big number with a small prefix, you always go to the base unit. So some's always going to get a 1. So if you have gram and kilogram, well, kilo is big, and it means 1,000. So the big number will go with a smaller prefix. So 1,000 goes with gram and 1 goes with kilogram. And that way you don't have to deal with these smaller numbers here. You can go with, you don't have to deal with the negative exponents. Okay, if you convert centimeters into meters, okay, so you just do those two. See, centa is your prefix because meters means you're measuring length. So what does C mean? It means centa, which means 100. Now, is centa bigger or smaller than your base unit? It's smaller, okay? So that means the 1 goes with centimeter and a, oh, I messed up. Let me erase that. So you're comparing centimeters with meters. The smaller prefix is centa, so that would be 100 goes there, and 1, because 100 is a bigger number with smaller prefix. These are conversions. You might need to print those off or write those down somewhere. I would give you, I expect you to memorize the conversions we just saw, the SI units, okay, the base units. Any of these I would give you, okay? So I would provide those for you in a problem. Volume is 3 dimensions, so you have to do, have you ever seen like 1 centimeter cubed equals 1 milliliter? You might want to write that down and know that, because if you go to, like say you have a baby and the doctor tells you you need to give them 3 cc's. Okay, have you ever seen that, 3 cc's? And then you go and they give you like a little, what do you call that, like a little syringe. And then on the syringe you see milliliters. Well, the cc is cubic centimeter. And that's the same thing as 3 milliliters. But so you get on the syringe and you're like, okay, there's my 3 milliliters. You see? That's the conversion, because volume is, what is volume? Length times width times height. So 1 centimeter by 1 centimeter by 1 centimeter is 1 centimeter cubed. And that equals 1 milliliter. And so if you took the 1 centimeter by 1 centimeter by 1 centimeter and you filled that up with water, that's the same thing as 1 milliliter. So this is a way to measure volume in the volumetric flask, burette, pipette. To measure volume, which is done usually in milliliters or centimeters cubed or liters in the laboratory. These are examples of length. You see they're all meters, volume, liters, and mass is grams. So get used to what those units represent. And we will stop there.